we will produce a given strain. So what is the relationship that links those two? That's what we're going to try to solve. And that's going to be linked in its simplest form to linear elasticity. So let's go to linear elasticity, finding the parameters that are going to allow us to make this link possible. Let's imagine a solid, and I'm going to make it a little bit longer in one direction, but it's exactly the same. This is just for experimental reasons. But here I'm going to have a solid. I have a coordinate system, 1, 2, 3, and I'm not going to let this solid to go down. I'm going to put rollers on the bottom of the solid everywhere. So it cannot go down, but it can displace in directions 1 and 2. And to that solid, I'm going to apply a stress which is going to be a bunch of tiny forces called sigma 3, 3. Notice that it's sigma 3, 3 because it's applied on phase number 3, on direction number 3, and it is a compression. So, what am I going to get as a result of that? A deformation, right? So if I apply just compression on one side, what you would expect is as that solid over there, it's similar to the one we have here, and if I apply stress in this direction, and let me try to look for the lag, right? As I compress it, it's going to get shorter in one direction, but notice very important too, it's going to get longer in the transverse direction, right? How is that called? You guys remember the name of that effect?
Poisson's ratio.
The Poisson's effect, you call it Poisson's effect, and it depends on the value of the Poisson's ratio. So it's going to get shorter in one direction and bigger in the other direction. Well, let's go step by step, okay? The change in direction 3 divided the original length in direction 3 is going to give me the strain in direction 3, right? With the equations we just defined, we said that this is going to be the strain direction 3, and assuming linear elasticity, I'm going to define the Young modulus, and this is the definition, okay? Something I came up with right now. I'm going to say that the Young modulus is going to be equal to the strain, which I defined it before, divided the stress in direction 3. So this is the definition, and that's what we call the Young's modulus. Probably you remember the other expression for there's a mistake here, guys. You see the mistake?
Yeah. It's not 3.
What is the mistake?
Stress over stress.
Stress over strain, right? You know how I notice that? Something that you should do always in your problems too. Because of the unit compatibility. I have MPA here and MPA over there. So Probably you remember this equation a little bit better by saying that stress is equal to Young modulus times strain. But actually how you define it is like this. And this is the Young modulus. Okay, before we go to the experiment, we were talking about the Poisson ratio, right? Now we have a way to quantify what would be epsilon 33 if we know sigma 33, right? For example, if we knew the Young modulus and we knew what stress we applied, this is going to be simply the stress divided the Young modulus. Okay, second definition is the Poisson ratio. The Poisson ratio is going to be defined as the ratio between the strain in direction perpendicular to the load, and in this case, just let me choose 1, 1, but it could be also 2, 2, divided the strain in the direction parallel to the load. Parallel to the load, in this case, sigma 33, we have epsilon 33, and perpendicular to the load, we have epsilon 1, 1. So notice that as we showed in this example before, if we have compression in one direction, the Poisson effect tells me that we're going to have extension in the direction perpendicular to it. And those strains, they are not going to have the same sign. Compression we assume positive, and extension we assume negative. And the Poisson ratio is, for convenience, defined as a positive number, and that's why we put a negative sign here. Because in our example, epsilon 33 is going to be positive, because if it is a compression, epsilon 1, 1 and epsilon 2, 2 is going to be an extension. This is the Poisson's ratio. And it's very important that that you remember that these two definitions are valid only when you have something which is called unconfined loading, and let's add just in one direction. So we have loading just in direction 3, and we let the solid expand in the other two directions. That's what is called unconfined, because it expands in 1 and 2, and in one direction because we just have stress in one direction. That's how we define the Young modulus and the Poisson ratio. We're going to see later on that these are not the conditions in which we have rocks in the subsurface. So we have to use another parameters or a combination of these parameters in order to represent other processes that we're interested in. Okay, so I propose that we measure the Young modulus of the rocks I brought over here. And that's why I have this small load frame. Our objective is going to be to determine the Young modulus and to verify that stresses increase with strain. So just give me 1 second. I'm going to set this up. This was an instrument that was the part of the acquisition, this part. Jeffrey did it. And this small load frame probably is more than 50 years old. Probably more than that. Okay, so just give me 1 sec. I'm going to find the right example.
It's a good.
Okay, this looks like a good one. Okay, so I'm gonna have to